Good morning, everyone. I hope you are enjoying your second consecutive snow day and that you had a chance to look at the central limit theorem demo video on my YouTube channel. That was the video that showed Fathom taking samples of different sizes from different shaped populations and seeing what the sampling distribution of sample means look like. Hopefully from that video you saw that if the population distribution is normal, then the sampling distribution of sample means is also normal, and that is irregardless of sample size, which seems to make sense. So if a population is normally distributed with a mean of mu and a standard deviation of sigma, we know the distributions of sample means is also normally distributed with a mean of mu, and the standard deviation is dependent upon the sample size. The larger the sample size, the less variability that we see. And this is provided the 10% condition is met, that we sample no more than 10% of the population. Let's take a look at an example. Here we have dry roasted shelled peanuts that are placed in jars. The distribution of weights is approximately normal and has a mean of 16.1 ounces and a standard deviation of 0.15 ounces. Without doing any calculation, explain which outcome is more likely, randomly selecting a single jar and finding the contents to weigh less than 16 ounces, or randomly selecting 10 jars, so the sample size of 10, and finding the average contents to weigh less than 16 ounces. Take a second to think about that. And without really doing any calculations, it seems to make sense that it would be more likely to find a single jar weighing less than 16 ounces, since that's between 0 and 1 standard deviations below the mean, than 10 jars. We know that the standard deviation of the distribution of sample means will be smaller for 10 jars than for a single jar. So I would say, which outcome is more likely? I would say that this one is more likely, but let's actually do some calculations. Let's start by finding the z-score for selecting a single jar. So that means we take mu minus, or actually our value that we're looking for, 16 minus mu, and then divide it by our standard deviation. And when we do this calculation, we get a z-score of about negative 0.67. And you can look that up on table A or use your calculator. The probability associated with that is about 0.252, so about 25%, which seems to make sense. Now let's take a look at the z-score for a sample size of 10 jars. So once again, we'll do 16 minus 16.1 for our numerator. And for our denominator, we need to find the standard deviation for the distribution of sample means based on a sample size of 10. So I need to actually take the population standard deviation of 0.15 and divide it by the square root of our sample size, which was 10. And when we do this calculation for z-score, we get a z-score of negative 2.13. And we know that a z-score of negative 2.13 is further out in the tail than a z-score of negative 0.67. And the probability that's associated with this, if you look this z-score up on the table or use your calculator, is about 0.017, or about 2%. So it's definitely more unlikely to observe a set of 10 jars with a mean weight of 16 ounces versus selecting a single jar and finding it to weigh less than 16 ounces. All right, the next thing I'd like us to take a look at is a strange population, one that's not normally distributed. So what do you think a sample distribution of sample means will look like for sample sizes of 2 from this? Or size 5, or size 25? Well, let's think about 2 for a second. We might pick one of each, which means the average would be in the middle, or maybe we'll pick 2 low ones or 2 high ones. So I think we'd have a bulk in the middle and then 2 other peaks, so maybe 3 peaks for a sample size of 2. A sample size of 5, maybe something similar, a big peak in the middle and then 2 peaks on the other side. And then if we happen to select 5 really small ones or 5 really large ones, we'd have little tiny peaks on the left and right. And for 25, I I wonder what that would look like. Let's take a look. So I used this applet at Rice University. I'll show it to you really quickly here. If you just type Rice University Sampling Distribution Applet and click on the first one, you might have to update your Java for this and tell it to run. Click on Begin. So let's say that our distribution is custom. So let's give it a weird shape. I can paint the distribution with my mouse. Kind of do the distribution like we did in the notes. And let's take a sample of size 5. And I'm just going to do animated here. So there's 5, and there's the sample mean. And there's another 5 and the sample mean, and so on. Let's do 1,000 of those. With a sample size of 5, we have we have 5 peaks, like I said. I wonder if our sample size was 2. Let's try that. 1,000 samples of size 2. Yep, there's 3 peaks because we get 2 in the middle, 2 low or 2 high. What about a sample size of 25? Let's see what that looks like. 1,000 samples of 25. That looks like it's almost approximately normal. Let's fit a normal curve over that. Not quite, but pretty close. Pretty close. So if you have a chance to play around with that applet, you should. It's kind of fun to paint different strange distributions and see that no matter what the population distribution looks like, if we take a large enough sample size, our distribution will be approximately normal. And different textbooks say a sample size of 20, a sample size of 25. We'll use a sample size actually of 30. That's what the central limit theorem says. So this picture kind of describes what I was just talking to you about. So as the sample size gets closer and closer to 30, the distribution of sample means becomes more and more like a normal distribution. I hope you have a chance to read Chapter 7, Section 3 of the textbook, and I also hope you had a chance to watch that previous video. If you didn't, I would recommend doing so. See you in class tomorrow.